Hi, in this last video about ODEs, we're going to discuss two advanced topics: adaptive methods and the shooting method for boundary value problems. Now, regarding adaptivity, the key idea is that in Runge-Kutta methods, the step size h may be changed at each step if needed. In other words, instead of using a uniform step size h, we may use non-equispaced basis points x0, x1, x2, dots, xi, xi plus 1, dots, where this step size hi may change from step to step. We simply need to take that into account in our algorithm, okay? As illustrated here, for instance, for the Runge-Kutta 4 method. Of course, if we want to change the step size, we need a criterion to do so, and what adaptive methods do is to control the local error and adapt the step size accordingly. Now, the most widely used adaptive Runge-Kutta method is the so-called Runge-Kutta-Feldberg method, okay, or RKF45, which can be understood as two Runge-Kutta methods in one, in the sense that the solution is computed with a method of order 4. The local error is estimated with a method of order 5, and if the local error is above a prescribed threshold, the step size h is decreased. This method is the one encoded inside command ode45 in MATLAB. Second topic we want to discuss are boundary value problems. Consider this second-order differential equation where f depends now in x, y, and also dy dx, and assume we have boundary conditions y at a equal ya, y at b equal yb. Okay. This is a boundary value problem because these two boundary conditions are prescribed at two different points. We have seen that numerical methods for ODEs, such as Euler's method or Runge-Kutta method, are designed to solve initial value problems. That is, problems where all conditions are given at the same point. For this reason, boundary value problems are solved as an iterative sequence of initial value problems. And this is done by means of the so-called shooting method. The idea is the following: we write an initial value problem with the two following initial conditions. The one given by the problem and another one on the slope where theta is not a problem input but a variable to be determined. And this is done by solving a root finding problem. The right value of theta is the one that makes the trajectory hit or meet the boundary condition y at b equal yb. This is graphically illustrated here. We start with an initial approximation for the slope theta 0 and shoot. By shoot, we mean we solve an initial value problem and check this value here. We compare this value here with the prescribed value yb. If our shot is too high, we then decrease slope in our second shot. Okay. Now we got below the target, and in this manner we use an iterative method to compute the correct value of this slope. For solving this root finding problem, we need to take into account that the analytical derivative of g is not available, so a secant method will be more convenient than a Newton method. And we need to take into account that every shot, that is, every evaluation of g, requires the solution of an initial value problem by using either a constant step size or an adaptive step size Runge-Kutta method, for instance.